Astronomy is big science. It's a vast universe out there, and the exploration of the cosmos requires huge instruments. This is the 5-meter Hale reflector on Paloma Mountain. When the European Southern Observatory came into being 50 years ago, it was the largest telescope in the world. ESO's Very Large Telescope at Cerro Paranal is the state-of-the-art now. As the most powerful observatory in history, it has revealed the full splendor of the universe in which we live. But astronomers have set their sights on even bigger instruments, and ESO is realizing their dreams.
See that mountain over there? That's Cerro Amazonas. Not far from Paranal, it will be home to the largest telescope in the history of mankind. Meet the European Extremely Large Telescope, the world's biggest eye on the sky.
Sporting a mirror almost 40 meters across, the EELT simply dwarfs every telescope that preceded it. Almost 800 computer-controlled mirror segments. Complex optics to provide the sharpest possible images. A dome as tall as a church steeple. The EELT is an exercise in superlatives. But the real wonder, of course, is in the universe out there. The EELT will reveal planets orbiting other stars. Its spectrographs will sniff the atmosphere of these alien worlds, looking for biosignatures. Further away, the EELT will study individual stars in other galaxies. It's like meeting the inhabitants of neighboring cities for the first time. Working as a cosmic time machine, the giant telescope lets us look back billions of years to learn how everything began. And it may solve the riddle of the accelerating universe, the mysterious fact that galaxies are pushed away from each other faster and faster.
Astronomy is big science, and it's a science of big mysteries. Is there life beyond Earth? What's the origin of the universe? ESO's new monster telescope will help in our quest to understand. We're not there yet, but it won't take long. So what's next? Well, no one knows, but ESO is ready for the adventure.
Good evening. That was Dr. Joe Lisk. I would like to thank the European Southern Observatory, ESO, for sending me a selection of free education materials for use in the making of astronomy in space. They are very much appreciated and will be very useful. ESO is Europe's premier observatory in the Southern Hemisphere. This programme looks at the pioneers that led the way to the construction of ESO's Extremely Large Telescope and the Magellan Telescope in Chile, which will be operational by 2025. The Reflector telescope has come a long way over the last 350 years. During that time, there has been many changes to the design of the telescope mounting and the construction of the primary mirror. Many of you are the proud owners of a reflector telescope. These have the advantage over the refractor in two ways. The large aperture mirror not only allows you to gather much more light so you can see fainter stars, they also allow you to resolve finer details on the moon and planets. Visible light is actually a combination of different colours called a spectrum. Depending on the colour, blue light has a small wavelength and red has a large wavelength. The main advantage of the reflector is that all the colours are reflected and focused equally, so there is no false colour around the object being observed, an effect known as chromatic aberration. The resolving power for any telescope can be found by dividing the constant 4.56 by the aperture in inches. So, a 6-inch reflector can separate two stars 0.76 arc seconds apart, and an 8-inch reflector has a resolving power of 0.57 arc seconds. This is referred to as the Dawes limit, after the astronomer William Rutter Dawes, who first worked it out. In addition, the larger the aperture of the primary mirror, the fainter the stars that can be seen with the telescope. Therefore, a 6-inch reflector will show stars down to magnitude 13.6, and an 8-inch telescope will reveal stars to magnitude 14.5. In comparison, a pair of 10 by 50 binoculars will show stars as faint as the 11th magnitude. There are 3 types of reflector telescope, which are named after the inventor of the system: the Newtonian, the Herschelian, and the Gregorian. Each uses a concave mirror that collects the starlight and magnifies it. In the early years, this was made from speculum metal, an alloy of copper and tin. From around 1887, mirrors were made from glass which was silver-coated. Whatever the primary mirror was made of, it was important to grind it to the correct curvature for making good observations. Today's giant telescope mirrors are made from hexagonal mirror segments slotted together to make one big primary mirror. The first idea for a reflecting telescope did not come from Isaac Newton, but from a Scottish scientist named James Gregory in 1663. Gregory proposed to collect the light by means of a mirror and then reflect the rays back up the open tube onto a smaller concave secondary mirror. This secondary mirror would send the rays back down the tube once more, and they would pass through a hole in the centre of the main speculum, after which they would be brought to a focus and the image enlarged by an eyepiece in the usual way. A few years later, Isaac Newton took up the problem. He had already been concerned with investigations into the nature of light, and in 1666, when Cambridge University was closed because of the plague, and Newton was working at his home at Woolsthorpe in Lincolnshire, he had produced the first solar spectrum. Sunlight was passed through a hole in a screen and then through a glass prism, so that the light was spread out into a rainbow with red at the long wave end, through orange, yellow, green and blue to violet. It may be said that this was the real birth of the science of spectroscopy. The pattern of Newton's reflector was different from that of Gregory. After the incoming light had passed down the open tube and been reflected by the main mirror, it was sent onto a flat secondary mirror placed at an angle of 45 degrees. The rays were then sent to the side of the tube, where they were brought to a focus and the resulting image enlarged by an eyepiece. The fact that the secondary was bound to block a little of the incoming light could not be helped, and in fact it was not important. Newton's first reflector was completed around 1670. In 1671 he presented one to the Royal Society and it worked well. The main mirror was a little more than an inch in diameter and the whole length of the telescope was less than 7 inches, but the principle was absolutely sound and many modern telescopes, both amateur and professional, are straightforward Newtonians. The main difference is that the mirrors of today are made of glass, whereas Newton used speculum metal, an alloy of copper and tin. The early reflectors did not produce bright images, and another disadvantage was that the mirrors tarnished quickly and had to be regularly repolished, whereas refractors required practically no maintenance at all. Silver on glass mirrors did not come until the work of physicist Jean-Bernard Foucault in France many years after Newton's time. Another optical system was demonstrated in 1673 by a Frenchman named Cassegrain, about whose personal life virtually nothing is known. His telescope was really a modification of Gregory's. There was a hole in the main mirror, but the concave secondary was replaced by a small convex mirror closer in to the primary mirror. In later years, Cassegrains became very popular, and almost all computer-assisted go-to telescopes of today use this principle, largely because they are much shorter and more compact than Newtonians, and are therefore much easier to handle. The first really good reflector was made by John Hadley. In 1721 he produced an excellent 6-inch Newtonian with a focal length of 62 inches and presented it to the Royal Society. It was compared with Christian Huygens' 125-foot long aerial telescope in Paris, and it was found to be just as good in performance as well as being vastly more convenient to use. Hadley made a number of telescopes, mostly Newtonians, but also a few Gregorians and Cassegrains, and they became very popular. The next great advance came in the latter part of the 18th century and was due to the genius of one man, William Herschel. It has been claimed that William Herschel was the greatest of all astronomical observers, and this may well be true, but his early career gave no hint of what was to come. He was born Frederick William Herschel, the son of a bandmaster in the Hanoverian Guards, on the 15th of November 1738. Hanover was his hometown and he was educated there. He always intended to make music his main career, and he decided to try his luck in England with his brother Jacob, who arrived in London in the autumn of 1757. Apart from a few fleeting visits to the continent, the rest of his life was spent in England. He began earning money by copying music, but then he obtained a post as organist at Halifax in Yorkshire, and in 1766 he was appointed organist at the Octagon Chapel in the fashionable resort of Bath, and his real career began. In 1772 he brought his sister Caroline over from Hanover to keep house for him, and this too proved to be a good move. Caroline was a good singer and later became an excellent astronomer, discovering several comets as well as acting as her brother's assistant. Here are Caroline's notes of a comet she discovered on the night of the 1st of August 1786, which was then at magnitude 7.5. The comet first became visible to the unaided eye on the 17th of August. Herschel's interest in astronomy began around 1766, and he hired a small telescope, but it did not satisfy him, and for some years he had no spare time to devote to his new hobby. Then, in 1773, he moved into a house at New King Street, Bath. not number 19, which is the present Herschel Museum, and he decided to make a telescope for himself. He set up a small workshop in his house and began to experiment with mirrors. He had no helpers apart from Caroline and his brother Alexander, who had joined him from Hanover and was a capable mechanic, but his patience was infinite. Failure followed failure, but at last he produced a good telescope with a mirror 8 inches in diameter and a focal length of 5 feet. The optical system was conventionally Newtonian and the mirror was of speculum metal. On the 4th of March 1774, this new telescope was turned towards a great nebula in Orion, and Herschel's career was well and truly launched. Herschel began regular observing with the aim of finding out how the stars were arranged in space. This meant carrying out what is termed a review of the heavens, and it was during one of these, undertaken with a 6.2-inch reflector with a focal length of 7 feet, that he made his greatest discovery. Here is a page from Herschel's observation notebook showing the entry for Tuesday the 13th of March 1781, the night he discovered a new planet. While observing, he came across something which was definitely not a star. It showed a disk, which no star can do, and it moved slowly from one night to another. Herschel believed it to be a comet, which would be interesting but not vitally important, and indeed his initial paper to the Royal Society was entitled An Account of a Comet. Before long, the object was found to be a new planet, moving far beyond the orbit of Saturn, which was finally named Uranus after the first ruler of Olympus. Herschel next made an excellent reflector with a 12-inch mirror and a focal length of 20 feet, and another with the same focal length but a mirror over 18 inches in diameter. Here is a photo of the 18-inch mirror taken by Sir Patrick Moore in the Herschel Museum, Bath, which shows its large size. Imagine just how hard it was to make. He then decided upon a 36-inch with a focal length of 30 feet. The first step was to cast the metal blank, which was to be turned into the main speculum, and this was itself a major undertaking, particularly since no mirror of such a size had ever been made before. In the cellar of number 19, a mould was prepared using horse dung, and on the 11th of August 1781 all was ready. Unfortunately, the mould began to crack and the mirror blank was damaged. A second attempt ended in near disaster. Again the metal leaked through the mould and the fiery torrent spread across the floor, shattering the flagstones. Meanwhile, Herschel's recognition was spreading, and George III, who had ascended the throne in 1760, was a genuine enthusiast. In 1782, Herschel was invited to the court, and naturally he went. While in London, he paid a visit to the Royal Greenwich Observatory and showed one of his telescopes to the Astronomer Royal, Neville Maskelyne, and Herschel became the most skillful mirror maker worldwide. Everything went well. Herschel was appointed King's Astronomer, not Astronomer Royal, and granted a pension which made it possible for him to give up music as a career and devote his whole time to astronomy. Once settled in Slough at Observatory House, Herschel planned a new telescope. It was to have a 49-inch mirror and a focal length of 40 feet, far bigger than any previous instrument. Making the mirror took some time. The first attempt was a failure, but the second was satisfactory, and it was this mirror which was always used. The sheet iron tube was so large that when it had been finished, and before the optics were installed, visitors were able to walk through it. On one occasion, the king did so, accompanied by the Archbishop of Canterbury. Apparently, the Archbishop stumbled, prompting the king to comment, "Come, my lord, and I will show you the way to heaven." The optical system was not Newtonian. Herschel decided to do away with the secondary mirror altogether and tilt the main speculum so that the image could be formed directly at the side of the top of the tube. Known as the Herschelian design, it has serious disadvantages. It is hard to adjust, and it also causes distortions, so that Herschelian telescopes are never used today. Almost as soon as the 40-foot was ready, it was responsible for the discovery of Saturn's two inner satellites, Mimas and Enceladus. It seemed that the great telescope was destined for a brilliant career. It was not to be. Certainly it was imposing. The tube was mounted on a wooden framework, and the whole structure could be rotated on a circular revolving base. Ladders 50 feet long gave access to the observer's platform at the top of the tube, and the observer communicated with his assistants through speaking tubes. Generally, of course, the chief assistant was Caroline, installed in a hut at the bottom of the structure, but at least two workmen had to be in attendance to move the telescope around. Sir William Herschel's other assistant was John Stone, who helped him with a survey of the northern sky. This resulted in the discovery of over 2,100 double stars, along with star clusters and nebulae. The telescope arrangement was awkward and clumsy, the mirror tarnished quickly, and keeping it in a fit state for use was a real problem. Almost all Herschel's work was done with a smaller telescope, and the 40-foot remained largely idle. The last recorded observation with it was in August 1815, when Herschel looked at Saturn and wrote, "The mirror is extremely tarnished." Well before Herschel's death in 1822, the telescope was dismantled. The telescope tube remained at Observatory House until the building itself was demolished in 1961. Here is a photo of the 40-inch mirror when it was discovered just before the house was sold for demolition. The bottom part of Herschel's telescope was on display at the Old Royal Greenwich Observatory for many years. In the 1830s, William's son John, himself a brilliant observer, took the 20-foot telescope to the Cape of Good Hope to survey the far southern sky. He set it up at Field Hazen, outside Cape Town. Its site is now marked by a monument in the grounds of the Grove Primary School. It was the first major observatory in the Southern Hemisphere, which today is superseded by ESO's Observatory Complex in Child, which is probably the best anywhere in the world. Another instrument maker was James Hall Nasmyth, who was born on the 19th of August 1808. He was a Scottish engineer and inventor famous for his development of the steam hammer. He was the co-founder of Nasmyth, Gaskill and Company, which made machine tools. After a successful career, Nasmyth retired from business in 1856 when he was 48 years old. He then settled down near Penshurst in Kent, where he renamed his retirement home Hammersfield and happily pursued his various hobbies, including astronomy. He built his own 20-inch reflecting telescope, in the process inventing the Nasmyth focus, and made detailed observations of the moon. The Nasmyth focus was similar in design to the Newtonian, except the secondary flat mirror was in line with the balanced axis of the telescope tube. This allowed the observer to stay comfortably in position as the telescope was pointed at various angles to view celestial sights. He co-wrote the book The Moon, considered as a planet, a world and a satellite, with James Carpenter. This book contains an interesting series of lunar photographs. Because photography was not yet advanced enough to take actual pictures of the moon, Nasmyth built plaster models based on his visual observations of the moon and then photographed the models. A crater on the moon is named after him. James Nasmyth died on the 7th of May 1890. We now come to the most extraordinary telescope in history, the 72-inch reflector at Bear Castle in the Republic of Ireland. Lord Oxmantown lived in Bear Castle in central Ireland, not very far from the town of Athlone, and it was here that he grew up. He went to Trinity College, Dublin, and then on to Magdalen College in Oxford. In 1822, he graduated with first-class honours in mathematics. After his marriage to Mary Wilmer Field of Heaton in Yorkshire, in 1836, his parents handed over Bear Castle. In 1828, Lord Oxmantown began taking astronomy really seriously. He soon realised the need for really large telescopes, and like Herschel before him, he considered the relative merits of reflectors and refractors. Also like Herschel, he settled upon the reflecting type. Lord Oxmantown decided to try his hand at mirror making. He had no apparatus, no skilled helpers, and nobody to advise him, so he was very much on his own. He enlisted the aid of a carpenter and a blacksmith, plus assorted farm labourers from the Bear estate, and began to make experiments on casting speculum mirrors. By 1839, he had made a good 36-inch mirror with a focal length of 30 feet and mounted it in the same way as Herschel had done for his main telescopes, apart from the fact he rejected the front view optical system and reverted to the conventional Newtonian. The 36-inch was only a beginning. To see into the depths of space, something even more powerful was needed. On the 13th of April 1842, the huge 72-inch mirror was successfully cast, and work upon figuring it could begin. By then, Lord Oxmantown had become the third Earl of Ross. The 72-inch mirror was twice as large as the 36-inch and was very heavy. To try to mount it on the Herschel pattern would have been sheer folly, and so a totally unconventional design was adopted. The 58-foot tube was to be mounted between two massive stone walls, each 70 feet long and 50 feet high, so that it could be turned only towards that part of the sky which lay near the meridian or north-south line. This meant that any particular star could be followed for only a limited period. For an object on the celestial equator, the total viewing time available was about an hour each night. Both before and after that period, the object would be hidden behind one or both of the stone walls. This was unfortunate, but not as disastrous as might be thought, because a star is at its highest when on the meridian and less affected by the unsteadiness of the Earth's atmosphere. During 1843 and 1844, work went on apace. When completed, the observatory looked very strange. The base of the actual mounting for the telescope was to be a massive joint of cast iron, and on it was bolted a square wooden box 8 feet wide, carrying the speculum. This box in turn carried the tube, which when vertical looked rather like an old Irish round tower. The tube itself was 8 feet across in the middle, tapering to 7 feet at either end. It was made from inch-thick deal staves, hooped with iron clamp rings and strengthened by iron diaphragms. At the top, the secondary mirror, which was so heavy it had to be counterpoised. The movement in declination was accomplished by means of strong cable chain fixed to the top of the telescope, passing over a pulley fixed at a suitable height, and then down to a winding handle on the ground operated by two assistants. The quick movement in right ascension was controlled from below by means of a wheel turned by yet another assistant. For each motion there were fine adjustments so that the mirror movement needed to keep an object in view could be made by the observer who was actually using the telescope. There was no finder telescope. Objects were located using a low-power wide-field eyepiece, and this must in itself have been a remarkable degree of skill. The 72-inch was generally known as the Leviathan of Parsonstown, and this nickname is still often used today. By 1845, the telescope was ready, but there was a delay in starting a full program of observation because this was the time of the potato famine in Ireland, and Lord Rosse was busy in relief work. It was 1848 before observing really got underway, but even before then the first major discovery had been made. Once the telescope was in full operation, Lord Rosse began an energetic observing program, and his clear nights were not wasted. However, there were continuing problems. It was far from easy to keep a 72-inch mirror in peak condition. It tarnished quickly, particularly in view of the damp climate of Central Ireland, and there were times when the telescope underperformed. Yet, despite all of this, it was very good indeed. One needs only to look at the Rosse drawings of the spiral galaxies, which are uncannily similar to modern photographs. Of course, the nebulae were not the only targets. The Rosse drawings of the planets were as good as any previously made, and there were particularly good representations of Jupiter and Mars. For the detection of very faint objects, the Leviathan was in a class of its own. Its light grasp was far superior to that of any other telescope of the time. We now turn our attention to America. In 1891, a young American, George Ellery Hale, invented a new type of instrument, the spectroheliograph, which could produce images of the sun in the light of one selected wavelength, principally hydrogen. In 1892, Hale was appointed Professor of Astronomy at the University of Chicago and began to plan the establishment of a new observatory. Money was needed, and Hale enlisted the aid of a local millionaire, Charles T. Yerkes, who provided the finance for a 40-inch refractor, which is still the largest telescope of its kind in the world. The Clark objective lens was of superb quality, but Hale saw that as far as refractors were concerned, the limit in size had been reached. The lens had to be supported around its rim so that larger sized lenses would distort under their own weight and would be useless. To look into the depths of the universe, Hale needed a much larger telescope, and it had to be a reflector. His constant call was for more light. He aimed for a 60-inch reflector. Again he was lucky. He approached the Carnegie Foundation, a powerful financial trust, and was promised enough money to build a 60-inch. George Willis Ritchley, at that time was a superb mirror maker, was put in charge of the optical side of the venture, and work began in earnest. He aimed for a 60-inch reflector. Again he was lucky. He approached the Carnegie Foundation, a powerful financial trust, and was promised enough money to build a 60-inch telescope. George Willis Ritchley, at that time a superb mirror maker, was put in charge of the optical side of the venture, and where it began in earnest. The choice of the site was of vital importance. Altitude would be an advantage, and there were two mountains in California which looked as though they might be suitable. One was Mount Wilson, overlooking the city of Los Angeles. The other was Palomar, much further away from any major centre of population. Palomar was certainly the better, but it was much more difficult to access, and so Mount Wilson was chosen. The 60-inch was finished in 1908. It was not as large as Lord Ross's Leviathan, but it was of a completely different design. It had a silvered mirror, it could reach any part of the sky, its mounting was amazingly precise, and it had a very accurate drive. The mounting was a skeleton construction. After all, the only use of a telescope tube, whatever its design, is to hold the optics in the correct positions. Even before the 60-inch came into operation, Hale was making new plans. Why not a 100-inch reflector? Once again, he cast around for financial backing, and once more he found one, John D. Hooker, a Los Angeles millionaire. Making such a colossal telescope was a daunting task, and when the mirror blank had been cast, it took Ritchley and his team 6 years to figure it to a required optical curve. The mounting was its so-called English type. The telescope was mounted on a massive beam fixed at both ends, and it was extremely stable. The main disadvantage being that the telescope could not be turned to regions close to the celestial pole. For the next 30 years, the 100-inch was not only the largest telescope in the world, but it was in a class of its own, so that it could show objects much too faint to be seen with any other instrument. It was with the 100-inch that one of the greatest of all astronomical discoveries was made. The realization that the starry nebulae, listed by the French astronomer Charles Messier and drawn so painstakingly by Lord Rosse, are indeed independent galaxies. Measuring star distances was never an easy matter. Frederick William Bessel had the first success in 1838 when he found that the dim star 61 Cygni is around 11 light-years away. Bessel had used a method of parallax. The object is viewed from the opposite ends of a baseline, and the slight difference in direction makes it easy to work out the required distance by simple mathematics. For 61 Cygni, Bessel's baseline was the diameter of the Earth's orbit, 186 million miles. The star shifted in apparent position by less than 0.3 of an arc-second, but this was enough for Bessel to obtain a very accurate result. Unfortunately, the parallax method works out to only a few hundred light-years. Further out, the parallax shifts become so small that they are swamped by unavoidable errors in observation, and the spirals were much further away than that. However, there was a solution, thanks to some convenient stars known as Cepheid variables. The name comes from Delta Cephei, the first discovered member of the class, which lies in the far north of the sky. Here is a star chart of the constellation of Cephus, the king, and the prototype star Delta Cephei is indicated by the arrow. Unlike normal stars, Cepheids do not shine steadily. They brighten and fade with clockwork regularity, and it had already been found that the real luminosity of a Cepheid is linked to its period of variation. The longer the period, the more luminous the star. Thus, Delta Cephei itself, with a period of just over 5 days, is less powerful than Eta Aquila, where the period is over 7 days. When the true luminosity is known, the distance can be found. Edwin Hubble, one of the astronomers at Mount Wilson, set out to locate Cepheids in the spirals. Only the 100-inch telescope was powerful enough for the purpose, but in 1923 Hubble was able to identify Cepheids in several of the spiral galaxies, including Messier 31 in Andromeda. As soon as he measured their periods, he realized they were much too remote to be members of our own galaxy. He derived the distance for the Andromeda spiral at 900,000 light years, later reduced to 750,000 light years. In fact, this was later found to be an underestimate, but the main problem had been definitely solved. The next advance was also made possible by the light grasp of the 100-inch telescope. Together with his colleague Milton Hamerson, he studied the spectra of the object which is now known to be galaxies. The spectrum of a galaxy is made up of a combined spectra of many millions of stars and is bound to be something of a jumble, but the main Fraunhofer lines can be made out and their positions measured. According to the well-known Doppler effect, the apparent wavelength of light source is affected by its motion relative to the observer. With an approaching object, all the spectral lines will be shifted over to the blue or shortwave end of the rainbow band, while with a receding object, the shift will be towards the red. Hubble and Hamerson found that apart from a few very close systems, including the Andromeda spiral, all the shifts were towards the red, so that every group of galaxies was racing away from each other. The universe was expanding. That is not all. The further away a galaxy is, the faster it is receding. There is a definite law, known as the Hubble constant, that once the red shift has been found, the distance automatically follows. Today we can identify systems so far away that their light takes over 1 billion years to reach us. Hale was never satisfied. Even after the triumphs of the 100-inch, he yearned for something even larger, a 200-inch this time. As usual, finance was the first hurdle, and once more, Hale overcome it. He went to the Carnegie Institute of Washington and obtained an initial grant of $6 million with the promise of more to come. Years before, Hale had considered Palomar Mountain and had rejected it only because of its inaccessibility. Since then, transport had become more easier, and Palomar was certainly a much better site than Mount Wilson, so Palomar was chosen. It is over 7,000 feet high and well away from any serious light pollution. So far as the mirror was concerned, quartz would have been ideal, but after a long series of experiments, it was reluctantly decided that the problem of making a quartz mirror was too great, and Pyrex was used. The first attempt at casting the blank was made on the 25th of March 1934. The mound containing 65 tons of molten Pyrex took more than 2 weeks to fill and a further 16 days to heat to the required temperature, after which there was a slow, regular cooling to room heat. When the blank was ready, it was found there was internal strains in the glass. Wisely, it was decided to keep the first blank as a spare and try again. This time, all went well, and the blank was taken to Pasadena in California to be figured. It was, of course, to be used as a Cassegrain, and Hale commented that the hole in the center of the speculum was as large as the entire objective lens of the Yerkes refractor. Figuring the mirror proved to be even more difficult than he had anticipated, and it took a very long time. Hale sadly did not live to see the 200-inch completed. He died in 1938, and there were other delays when the United States was drawn into the war in 1941. So it was not until the 3rd of June 1948 that the 200-inch, appropriately named in honour of Hale, was dedicated. Drive up the winding road to the top of Palomar Mountain and you'll come to within the side of the huge dome with surprising suddenness. It is 137 feet in diameter and weighs 1,000 tons. Go inside and the first thing you will see is what looks like a giant horseshoe. This is the mounting of a telescope, very different from the design adopted for the 100-inch. Although it weighs 500 tons, it can be moved around slowly and with absolute precision. Inside is mounted the telescope itself, which, like the 60-inch and the 100-inch, has a skeleton tube with a main mirror at the bottom. The tube is so large that when using the prime focus system, there is no need for a secondary mirror. The observer can sit in a cage actually inside the telescope. Before long, it was clear that the Hale telescope would be just as prevailing as the Hooker reflector had been in its time. It too was in a class of its own. Coming to the end of his career, George Ellery Hale died in 1953, and his mantle fell upon Walter Baade, a German astronomer who had emigrated to America before the war and had joined the Mount Wilson staff as early as 1931. Like Hubble, he concentrated upon studies of galaxies, and the 200-inch increased his scope enormously. In 1952, he discovered that there was a serious error in the Cepheid scale. There are two different classes of short-period variables, and they have different period luminosity laws. Type 1 Cepheids are much more powerful than those of Type 2, and Hubble, through no fault of his own, had used the wrong type to make his estimates of distance. The variables which he had been using as standard candles were twice as luminous as he had believed, so that they had to be twice as far away. In one short research paper, Baade calmly doubles the size of the universe. The distance of the Andromeda spiral was not a mere 750,000 light years. The real value was over 2 million light years. The extra light grasp of the 200-inch meant that Cepheids could be detected in galaxies which were much further away than those of the local group. The telescope could also show details quite beyond the range of any other instrument. There was another factor also to be taken into consideration: improvements in ground techniques. Electronics began to take over. What is termed CCD, or charge coupled device, is much more sensitive than any photographic plate, and the 200-inch was well able to adapt to these new techniques. By now, the observer no longer had to spend long hours in a cold, lonely observing cage. He can sit in the comfort of a control room, a cup of coffee by his side, and watch the results coming through on a television screen. The 200-inch, like the 100-inch, was designed for deep space research and was not concerned with the solar system. A few photographs of the planets were taken, mainly to satisfy public curiosity, but that was all. There was much more important things for the telescope to do. Of course, the 200-inch is by no means the only major instrument at Mount Palomar. There is also a Schmidt camera, which is of the greatest importance. All very large telescopes have one common weakness. Their fields are very small, so that to make a photographic survey of the whole sky would take a very long time. In 1930, an entirely new optical system was developed by an Estonian researcher, Bernard Schmidt. On the Schmidt system, the incoming light is collected by a mirror which is spherical and not parabolic, as with an ordinary telescope. Normally, this would introduce serious distortions, but these are removed by means of a thin glass plate with very complex profiles, fixed to the upper end of a tube. The photographic plate is situated at the focus. Normally, this would introduce serious distortions, but these are removed by means of a thin glass plate with a very complex profile, fixed at the upper end of the tube. The photographic plate is situated at the prime focus. The main problem is that the focal plane is curved, and so the special plate holder has to be used to bend the plate into the correct form. The end result is that sharp star images can be obtained over very wide fields, often well over 10 degrees across. The Ocean-Smith camera at Palomar has a 48-inch mirror. It was completed about the same time as 200-inch and has been in constant use ever since. Only the 53-inch Smith at the Karl Schwarzschild Observatory in Teutoburg in Germany is larger. In the 1990s, new powerful computers began to come into use at the world's largest observatories. Not only could these accurately guide the giant reflectors to their celestial objects, the computer allows the telescope to follow the object very precisely across the sky. This means that azimuth-type mountings can now be employed in telescope design, reducing the manufacturing costs considerably. As computers improved, a new astronomical technique was developed called adaptive optics, which allows thinner primary mirrors to be manipulated to counteract the poor seeing conditions of the Earth's atmosphere. It is also no longer necessary to construct telescope mirrors in one piece. Today the complete mirror is manufactured in manageable hexagonal sections that are slotted together. This allows the mechanism for the adaptive optics process to be easily fitted to the back of each segment, which again reduces the manufacturing costs. This brings us to the European Southern Observatory's extremely large telescope now under construction in Chile, which will have a primary mirror over 1,400 inches in diameter, which is 7 times larger than that of a 200-inch Hale reflector at Palomar in the United States. The first light on the telescope is expected in 2026. Finally, there will be the giant Magellan telescope, which is now under construction in Chile. It consists of 7 27.5-foot primary mirror segments with a resolving power of an 80-foot main mirror and a collecting area equivalent to a 72-foot one. The telescope is expected to have the resolving power of 10 times greater than the Hubble Space Telescope. When it is completed in 2020, it will be the largest optical observatory in the world. So, there is much to look forward to. These new extremely large telescopes will allow astronomers to look further into the universe to make more remarkable discoveries. Astronomers will for the first time get to see Earth-like planets orbiting around nearby stars. A fitting tribute indeed to the pioneers that have made reflector telescopes a reality. That is all we have time for this month. Please visit our website, Astronomy and Space Blogspot, where you can watch all of the past shows. And if you like this program, please share it with your friends and members of your local astronomical society. Until we come back next month, thank you for watching. Good evening.